Viewers are welcome to continuation of our discussions on topics in abstract algebra, where we continue to give actually highlights of the general notations as used in permutation groups. So you are welcome to illustration. Even and odd cycles. In the general notation, we are going to define what we call even cycle and odd cycle. So let me begin with even. Definition 1. A cycle is called even if it has odd length. Okay. In other words, a cycle is even if it has odd length. Example, if I give you a cycle 1, 2, 3. This is an example of an even cycle. Okay. Another definition for even cycle is that a cycle is even if it can be expressed as a product of odd number of transposition, and we know what transposition is. So if you want 1, 2, and 2, 3, this cycle can be written as a product of two transpositions. Because the number of transpositions is even, it is odd. The length is odd. Second, we define length as the number of points in a cycle. You can see the number of points here, 1, 2, 3. And see, this is an odd number. So this is, since the length is odd, the cycle is actually even. We have now the second definition. That will take us to definition 2, that a cycle is called an odd cycle. Odd. Okay, just like we had even here. If it has an even length. Okay. Example, if you have 1, 2, 3, 4. This is an example of odd cycle. Why? Because the length of this cycle is 1, 2, 3, 4 is 4, and 4 is an even number. So that means the cycle is odd cycle. Now, on the basis of cycles being odd or even, we now categorize the symmetric group. It follows that the symmetric group, what we call symmetric omega, is composed of an equal number of odd and even cycles. Okay, so that means if you now, and on the basis of this, we have another definition here to call the alternating group. Alternating. Now, an alternating group is a subgroup of symmetric omega. That is subgroup of symmetric group omega, in which has is made up of even cycles. So all the cycles, all the elements are even, and if you combine them together, they will give you an alternating group. I'll give you example. Let me take S3, the symmetric group of degree 3. Okay, this is a group containing identity element 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. Okay, how many? 1, 2, 3, 4, 5, 6. Okay, 6 elements. It follows that the A3, that means the alternating group of order 3, is a group containing identity 1, 2, 3, and 1, 3, 2. And by A3 we mean alternating group, okay, of degree 3, okay, of degree 3, okay. It has how many elements? 1, 2, 3, and they are all odd. This is odd because this is even, sorry, because it has odd lengths. This is also even because it has odd lengths. Identity element by convention is considered to be both odd and even. So, yeah, welcome to next presentation.